Basically, light as a reagent, like how can you use light and where is it actually useful? So the way old dye-sensed solar cells where you can actually use photosensitizers where light is actually used to excite them, or photoredox catalysis, which is very famous in organic chemistry, which started with ruthenium tris bip by Macmillan. And you can use it in organic solar cells and also fluorescent sensors. But the main ingredient of all this is actually photosensitizer. So I'm going to talk few slides like how to actually select a photosensitizer and how can you monitor different types of photo reactions that are going to happen in a photosensitizer. So basically I keep this slide as an introduction to everything, like what is a light harvesting system which actually contains an electron donor, linker and an acceptor. Once you excite an electron donor, there will be electron transfer from donor to acceptor, and we call it as charge separation. And of course the electron doesn't stay at electron acceptor, it comes back, and we call it as charge recombination. And if you keep, this is a light harvesting system or a donor acceptor system, and we can use different types of electron donors and acceptors, and which we call it as artificial photosynthetic system. And the same thing if you put it between two electrodes. It's not that easy, the fabrication, but I'm just giving a schematics that if you put between this, then we call it as a dye-sensed solar cell with different types of electron donors and acceptors, and the same thing you can actually utilize it for water splitting or hydrogen generation. So with this concept, again, this is a Jablonski diagram that we actually saw in our 10+2 or in bachelors, where you actually have an absorption and fluorescence, and the difference between an absorption and emission, which we call it as a Stokes shift. So the question comes is like, how do you measure an homolume gap in an absorption, or whatever you are actually getting, is it an absolute value or not? So whatever that you get from an absorption spectroscopy is actually only a gap. It doesn't give you where the HOMO is and where the LUMO is, and we take the help of electrochemistry. Again, electrochemistry is basically with respect to an electrode or in a solution. So, but the onset potentials will actually give you the oxidation and reduction potentials. And these are basically for the BSc and MSc students who are attending the talk today. Or then we take the help of computational chemistry, where you can actually calculate the HOMO and LUMO of these donor acceptor systems. But again, in the gaseous state, you can incorporate solvent systems in it. But again, this doesn't give you an experimental value. So really, like what we are actually going to say, so we can get cyclic voltammetry can give you HOMO LUMO, but if the light is involved in excitation, then don't we need to deal with the excited state? Yes, we need to deal with the excited states. Then if you really need to deal with the excited states, we cannot rely on ground state potentials. You actually go for an excited state potentials. When you go with an excited state potential, like for example, either you take an excited state oxidation potential or excited state reduction potential, it needs a ground state oxidation and reduction potential with E00, where E00 that you calculate is from the longer wavelength in absorption and lower wavelength or the first peak in emission. So with this, you can actually calculate whether something can donate electrons or not. Like for example, you can design a sensitizer based on it. Let's say either it is an organic reaction, or it can be a solar cell, or it can be any kind of catalysis that you are going to do. You can actually design the photocatalyst based on these properties. So you excite the sensitizer, then it can go. So that means you can actually calculate where the excited state oxidation potential is going to happen, whether it can inject that electron to TaO2 or not. Here I take an example of dye-sensed solar cell. So I mean, this is simple again for a textbook chemistry that you can teach for master's students, and which works perfectly, that you can say whether a molecule, in this case we have a dye here which is porphyrin, whether it can inject an electron into TaO2 or not. You can simply start from our textbook chemistry and then calculate it, and works perfectly. So this you can see, that way you can actually calculate for all the dyes that you can see, and you can select a perfect sensitizer based on this, that you can calculate an excited state oxidation potential, and you can take care of the lifetime also, which you can get it from ultrafast spectroscopy. So this is basically the introduction that I thought that I will do it before I go into the real chemistry that we are doing in our laboratory. So we talk about photo-induced hole or electron transfer, where you can actually excite the donor or acceptor, doesn't matter. In this case, you are exciting the acceptor. So, and there will be electron transfer. You will end up with donor cation radical and acceptor anion radical. Or when you excite the donor, again this gets excited and the electron is donated to acceptor. but the product is same. It's a donor cation radical and acceptor anion radical. So if light-induced electron transfer takes place in a donor-acceptor system, despite of the excitation of either donor or acceptor, quenching of the excited state takes place by the formation of charge-separated state. So this is the main important statement that we can actually do. So in a way, if you are selecting a photocatalyst, really it doesn't matter that's a oxidative quenching or a reductive quenching, it matters, but you have to see the excited state oxidation reduction potentials, and based on that you have to select it. Okay, that will actually decrease your load of making different types of photosensitizers. So then you can even calculate delta G of charge separation by using a Riemann-Wheeler equation, and this will tell you whether in a particular solvent whether electron transfer is possible or not. Basically in photoredox catalysis we do with photosensitizer is diffusion based photosensitizer, so it's not covalently connected. So electron transfer is much more tough in a diffused based photo where it is non-covalently bound and it is revolving in solution. So it is very hard to say whether the electron transfer can take place or not. So such kind of things, these calculations will quite help in those kind of studies. So today I'm going to talk about bispirolic systems, which are one of the best photosensitizers that we have been working on recently because of so many properties like photophysical properties, such as their molar extinction coefficients are very high and they are robust, they are air stable, and you can actually use it. Like for example, if you can modify them, which I have it in the next slide, you can modify them with different types of functionalizations. You can put it at meso position, pyrrole position, or in the methyl position, or on the fluorines. You can do different types of organic reactions, and you can actually do it, and you can control their singlet and triplet states. So or you can functionalize, if it is an azab ODP, you can functionalize either on the top or bottom, or you can actually functionalize at different positions. Okay, so then you can achieve different types of systems. So in today's seminar, I'll try to cover most of it based on like how can you use photo-induced electron transfer or energy transfer, or photo-induced electron transfer followed by energy transfer followed by electron transfer, and probably if there is time I can cover TICT, which is twisted intramolecular charge transfer. So the first one is photo-induced electron transfer in these systems. Like I don't want to go through it because I just went through this slide. So when you excite it, there will be electron transfer. So this is an electron donor and it's an acceptor. Okay, there will be electron transfer from this. Initially you can actually monitor the electron transfer from phenothiazine, this is a phenothiazine, to BODP by using a steady state fluorescence. Okay, the steady state fluorescence can actually say that if the quenching is actually taking place, okay, then electron transfer or the photo products are actually forming, or the charge separated state is actually forming. But photo-induced electron transfer is much more better in a polar solvent such as acetonitrile compared to that of hexane, and you can clearly see it, which is happening in this case. So then you can measure time resolved spectroscopy and to find out the lifetime of these compounds, and you can draw a energy level diagram which can give a clear picture whether a photocatalyst will work for certain reaction or certain for certain application or not. And the same thing, you can actually, the same donor acceptor system, you can apply it for different types of applications. You use it for different types of applications such as molecular sensing in this case. Again, the concept is pretty much same, that once you get excited, then usually initially it is coming back, there is fluorescence, but the moment you have a donor which is donating an electron, so usually this electron cannot come back because this is filled. As a result of that, the fluorescence is quenched. So in this case, I mean, I don't want to go through the whole text, but what I was trying to say is a reactive oxygen species which is hypochlorite. Okay, so I'm taking a normal donor acceptor system and I'm using it for hypochlorite sensing. Okay, and the concept is very simple, against photo-induced electron transfer. So there are different types of hypochlorite sensors available in the literature. Okay, but most of them either they are non-reusable. You cannot reuse them, at least even for one cycle, or they are actually made of costly metals such as ruthenium, or they are made of toxic metals such as selenium or tellurium. And once you make this selenium complex, there is a problem that it can even form dimers of BODP. So this is the same donor acceptor system I showed a few minutes back, where we were actually monitoring electron transfer. Now the moment you have hypochlorite, the sulfur actually becomes sulfoxide. Okay, and the fluorescence goes from totally dead fluorescence, because initially there was photo-induced electron transfer from phenothiazine to BODP, which we saw a few minutes back. Now there is no photo-induced electron transfer because this becomes a weak donor now. It's not going to donate the electrons to BODP, and as a result of that, the fluorescence actually gets enhanced. So the same concept, you can actually prove it. We were titrating with different types of different amounts of hypochlorite and seeing how the absorption is changing with not with the respect to absorption, but with respect to fluorescence. We could see a very good enhancement, what we saw in a cuvette, that the fluorescence is actually enhancing, okay, the moment you add hypochlorite. And we tested with different types of reactive oxygen species such as hypochlorite, hydrogen peroxide and different things, but it was very selective to hypochlorite sensing. And we try to monitor the products, whether it is sulfoxide or sulfone, and we did mass spectroscopy, and with mass spectroscopy we could find out that we could trap we could find out the intermediates such as sulfoxide or sulfone. But the main problem with this study was it was not water soluble. Okay, we were actually using little bit of DMSO in order to do it. Okay, the main idea is again same, it is photo-induced electron transfer that is happening, but the moment it becomes sulfoxide or sulfone, the HOMO is lowered, it is stabilized. So there is no electron transfer to HOMO of the BODP, and as a result of that, the fluorescence is not quenched, it is coming back. And it is a reusable sensor. At least for 3 cycles, we were able to use the sensor for hypochlorite sensing. And here we took one of the disinfectant that is available in the market called Harpic, and Harpic has hypochlorite, and we were able to detect hypochlorite even in the disinfectant which was available in the market, which is good. So we were happy with the results, visible, but we wanted to go for a visible or near air absorption, calorimetric or fluorescent or ratiometric sensor, but the most probable or most important thing that we wanted to do is a water solubility and reversibility. So this made us to go with same architecture of phenothiazine and BODP, but we have an acid groups and also PEG, polyethylene glycol groups, which made this compound more water soluble. So I am going to show this slide that where you have again no fluorescence, and the moment you add hypochlorite, it is highly fluorescent, and we took it all the way up to the paper strips, which you can detect hypochlorite directly on the paper strip or in the RO water, reverse osmosis water, where there is no hypochlorite. But even in tap water and disinfectant, we can see the fluorescence enhancement. And even the mass spectrometry also showed sulfoxide or sulfone, and we did with now as it is water soluble, we did with different types of reactive oxygen species, cations, anions, but you can see that it is highly selective to hypochlorite. But this made us to think like what is actually the species that is responsible for fluorescence enhancement. So what we did is the NMR, we took the help of NMR. So this diagram, this NMR spectra is only for the lab synthesized sulfoxide, whereas this is a titrated NMR. So you started with this compound, okay, whereas you have phenothiazine, and we keep on adding hypochlorite. At this stage, the NMR changes were not seen at around 2.4 equivalents, and we matched with the synthesized compounds NMR, and we could see that it is actually matching perfectly. So this says that mostly the fluorescence enhancement in this compound is because of the formation of sulfoxide, maybe less of sulfone. So this is where we are actually saying that a laboratory donor acceptor system, you can actually go into a real-time application of sensing. And we can use the same BODP systems, okay, for photo-driven water splitting also, which we did it with collaboration with Tom Mayer at University of North Carolina, Chapel Hill, and we will actually see the water oxidation, and in this case we did for the proof of concept with benzyl alcohol to benzaldehyde. So it's an oxidation reaction that we saw. So that was the concept of photo-induced electron transfer. So with the moment you go to photo-induced energy transfer, the idea is again same. When you excite the donor, the electron gets excited, okay, but again, when the energy, when the electron comes back, the energy is actually given to acceptor. Now the acceptor is actually going to get excited. So now initially it was excited donor, now it is an excited acceptor. So the beauty of this is you don't generate cation anion radicals, okay, and cation anion radicals are very dangerous, at least if you are trying to make some biological probes, because they are going to react with different types of biological systems. So again, you can calculate free energy of energy transfer using E00 values, and this is one of the system that we actually try to develop with a BODP system and a benzthiazole. When you can excite benzthiazole, there is photo-induced energy transfer. So this was actually established. So the main principle of FRET or photo-induced energy transfer is that you have the emission of benzthiazole and you have the absorption of BODP. If you can actually have an overlap of the emission and the absorption, okay, at least some overlap, then FRET can actually take place, which is photo-induced energy transfer can actually take place. And we actually applied this. We actually applied this in different types of solvents such as toluene, 1,2-dichlorobenzene, DMF, and acetonitrile. And you can see the fluorescence of benzthiazole is quenched, whereas the fluorescence of BODP actually enhanced. And this actually shows that photo-induced energy transfer is taking place in these systems. Then we took the help of transient absorption to really see whether this energy transfer is actually happening in the real time. Okay, so what that you can actually see the absorption of benzthiazole got excited and it gives emission around 440, and the emission of benzthiazole is actually gone, and you can see the emission of BODP, which is around 500 nanometers, and slowly that emission is actually slowly going to go. So which is going to really, result into bleaching. So this is a real-time application which is actually saying that the energy transfer is happening in the scale of nanoseconds. So then again, how to apply this energy transfer concept? So we were looking into, and the main idea was to apply to amylite binding, because benzthiozoles are known to bind to amyloids, okay, which are the main things for Alzheimer's disease. And one thing that we can see, it's a paper by Grass. It is written that heterocyclic nitrogen of THT, and hence the removal of positive charge increases the affinity of A-beta fibrils by a factor of 40. So this is a very famous probe for amyloids called THT, and because of this nitrogen, the positive charge on the nitrogen, it doesn't cross the BBB, blood-brain barrier. So if you can decrease, if you can remove this charge, you can actually use these systems for probes. So we actually made a water-soluble amyloid binding probe, where we made different types of probes, which these are unpublished results. We are actually planning to write a manuscript on this, and we can see the same energy transfer in all the polar solvents. But the one of the important slides that I want to show is, initially there is energy transfer, the red one, but the moment you add amyloid, okay, the energy transfer is actually increasing at least 2 to 3 folds, whereas the same with a control compound where you don't have benzthiazole, you don't see any enhancement. So we are actually using this for water soluble, and even it can actually bind to THT. It can replace THT, saying that the benzthiazole of our compound has a much more binding capacity compared to that of THT when it bound to amyloids. So the last thing which I have like couple of slides saying that now photo-induced energy transfer followed by electron transfer. So I was talking about PET, I was talking about PENT, now I'm talking about PET followed by PENT followed by PET. So this is one of the systems that we developed long time back, where you have benzthiazole, BODP, and porphyrin. So it absorbs at 250 to 350 nanometers, and BODP around 450 to 520. Then porphyrin is around 400 to 440. Then you have this system. So now once you have excite benzthiazole, there will be energy transfer followed by energy transfer followed by electron transfer. So that was actually the idea. So once, that means if you switch it on here around 290 nanometer, you will see electron transfer coming to fluorine, and we could prove it by using steady state fluorescence, where the emission is actually quenched, and we could prove it by transient absorption. The fluorine anion radical was actually found, saying that once you excite at 290, the fluorine anion radical is forming in a way that says that there is stepwise double electron energy transfer and then electron transfer. So with the same concept we made with AZA-BODPs with different types of donors, such as electron donors such as TPA and energy donors such as naphthalene. And the beauty of these systems is you can actually see it. The absorption is going all the way up to 1000. Okay, so we are almost in the near air region. So once you excite TPA, that naphthalene, then there will be energy transfer to AZA-BODP and followed by an electron transfer from the TPA. So AZA-BODP is acting like a relay of energy and electron transfer. So it doesn't matter where you excite, it is going to the energy is going to get stored in the AZA-BODP, and if you functionalize them with borons or iodines, you can use it for a photocatalyst, which goes to a triplet state, and it's an excellent robust photocatalyst. So this we could also establish that once you excite only TPA, there is only electron transfer now, energy transfer doesn't take place. So this is systematic, one by one we were actually doing with different types of model systems. Then we modified TPA with pyrines and keeping naphthalene constant. Again, even in this case you have PET from pyrene and PNT, which is energy transfer to azure body phase. So these are different types of things. Again, the fluorescence is quenched in this case, naphthalene, and you can see the fluorescence of TABPY. And this is an energy level diagram that we end up doing it. This is actually the end of our manuscript that we write all the time, is that once you excite pyrene, in this case, then pyrene will actually give electron transfer, then go to photo products. Or when you excite naphthalene, it gives energy transfer, then it comes all the way to an energy transfer product, which again will get an electron transfer from the ground state of pyrene. So at the end, everything will end up into anion and cation radical. Like I was saying, azure body P is actually, it will culminate into the azure body P molecule. So these are, with this I'm going to end my talk saying that you can actually make different types of systems such as TACT, twisted intramolecular charge transfer systems. Initially they are planar, but once you excite them, they actually get twisted. And its a charge separator state is more stable. Or you can, we have been working on Carol body P systems, porphyrin, benzyl porphyrin systems, and we use it for solar cells, and we used for trapping fullerenes, and BBA systems, which is one of the beautiful molecule where you can actually see a cation radical. Just I would like to say to the audience that it is very easy to monitor an anion radical because it usually comes at 1000 nanometers, but it's very hard to monitor a cation radical because it usually doesn't, it gets interfered with the triplet states. So as a result of that, we were actually trying to make a donor where you can monitor the cation radical, and this was one of the excellent donors we could make, which we actually used in these donor acceptor systems. Used it for dye-sensitive solar cells, different types of BBA fullerene molecules, BBA Carol molecules. Recently we have started working on Carols because Carols are very good catalysts for hydrogen evolution reactions. So at the end, I would like to summarize saying that we develop different types of solar energy harvesting materials. The concepts are pretty much same, which is photo-induced energy transfer or electron transfer. And we make different types of molecules such as artificial photosynthetic systems, molecular sensors, DSSC, and photo-driven water splitting. Of course, I would like to thank all our collaborators where I do photophysics from transient absorption and lifetime in ISCT, and computational studies with Tapta and Ravi and Pawar, and some biological study with Anu Sharma and Nimesh and Suresh. So this was my team at Central Institute of Rajasthan. Now currently it's a team at NIT Warangal. I think one of the student, Vijay, is working on Carol systems. He's sitting somewhere in the audience. And of course, definitely funding by different agencies. Right now I'm working on STARS funded project where amyloid binding stuff is taking place. So last slide is that this is NIT Warangal. This is our main building. This is chemistry department. This is library. And this is our, we call it as an arch, the Thoranam, where you actually get into the gate. And we have different types of courses, very well known for BTech, MSc in our general chemistry, integrated BSc, B.Ed, and integrated MSc and PhD in chemistry. And Warangal is a beautiful place. We have Kakatiya Fort, Ramappa Temple, 1000 Pillar Temple, and Bhadrakali Temple are very, very famous. With this, I thank everyone. Thank you very much.
The basic question. This linkers doesn't have double bonds.
No, yeah, I mean, if you have double bonds, it also works, okay? And the problem with double bonds is the moment you put double bonds, usually there is a twist, and it depends on whether you want which kind of thing. If you really want a PET or energy transfer, you really don't need a double bond, and it works through it, okay? It's always the space interaction or through bond interaction. It really doesn't matter. But if you put a double bond, usually you have twisted intramolecular charge transfer. Again, there is another problem with it. So depending on our need, we go with that. I mean, see, actually, if you see or if you want to go for organic synthesis, and if you want to usually use a visible light, okay, you want to have some dyes which can absorb in the near air region, but the most important thing is it should be only one system. You cannot use 2-3 systems. Okay, so if you look into our system like this is only one molecule which is absorbing from, like for example, I am talking about this molecule, molecule 1. It is absorbing, like the green one, you can see it is absorbing from 275 and all the way up to 1000. So it is very hard to put one donor acceptor system within a small molecule and use it. So this is one of the attempts that we made.
Long live India and France friendship.